So this video is about chromatograms. Chromatograms are the results that you get from an instrument that is performing chromatography. So I'm not talking about thin layer chromatography or that column chromatography with the sand in the um, burette, but I'm using an instrument that is identified as a chromatography type of instrument. So it's, thousands of dollars. And it's going to print out a picture. Now, again, if you took Gen Chem 2 at St. Charles Community College during a semester where labs were happening on campus, then you've seen chromatograms before. You used gas chromatography in the very first lab of the semester, where you put it in little tiny vials and then you put it in the instrument, and then you got this thing with these peaks, and that looked kind of like this. And so we're going to talk through chromatograms and then the important components of chromatograms, which are, again, that's the result. It's the what you get out of the instrument. So the chromatogram, it looks like a graph, but it's not true. I mean, the graph is the times along the x-axis, and the y-axis is whatever the detector response is. And we're going to get into that a little bit more in chapter 22. But for right now, it could be anything from absorbance, could be the y, or it could be like, just think of it like number of molecules or something. Okay. So the reason why time is the x-axis, because remember, we've got a mixture, and we're going to run it through our chromatography, our stationary phase and our mobile phase. It could be any of those 5 types of chromatography. So we're going to run it through our chromatography, and the compounds in the mixture are going to come out at different times. So in this example, there were 3 compounds in the mixture. If you look at this, there are 4 Hill thingies. Those Hill thingies are called peaks. The CH4 would be the mobile phase. So, injection time is like when you started it, when you put your sample on. So that was like the sample was introduced to the instrument. And then the first peak is how long it took for the mobile phase to get from the top of the, through the stationary phase and then to wherever the detector thing was. And then it took some longer time. The flat means nothing came out. And then we had one compound come out, a second one, and then a third one, and they would all come out at different times. Okay. And so time is a thing that we measure with this. So here's the picture. I'm going to go to the next slide and look at the definitions of what these symbols are, and then we'll come back. Okay, so T subscript R is called the retention time. It's the time it takes for that component to be retained on the stationary phase. So it's how long it takes for from the time that the sample was introduced to the instrument until it came out of the instrument and made it to the detector. So like in seconds or minutes. Okay. The retention volume would be the volume of mobile phase it took, like how much mobile phase the instrument had to use before that solvent or before that sample made it through. Okay. And on the last graph, there was a TM as well, which is the time for the mobile phase. Okay, so that's not containing the mixture at all. That's just pure mobile phase. Like that's the amount of time it takes for anything to move from the top of the stationary phase to the bottom of the stationary phase. Okay. The adjusted retention time, which is another symbol that we saw on that graph, has a little apostrophe there going on. It looks like retention time is TR and TM is the mobile phase time. So the adjusted retention time is just how much longer does the compound take than the mobile phase, because the mobile phase, remember, is the TM is the minimum amount of time for any compound to move from top to bottom. So, and TR is how long it takes from the moment your sample is introduced to the instrument until your sample, your component comes out of the bottom. So the adjusted retention time is just how much longer does the sample take than the solvent. Okay, so then the relative retention, which is the symbol alpha, is the ratio between, like if we have 2 components in the mixture, it's just the ratio of their adjusted retention times. How many times longer does this compound take than that compound? So I want to go back to the picture. So TM, this would be time 0, like when the sample was introduced. TM is how many minutes or seconds it took for the sample to go from the top of the column, which is where the stationary phase is, to the bottom of the column, to the detector. That's right there. So CH4 was our mobile phase in this example. And then looking at the unknown specifically, the retention time, the TR, is from time 0 to when the peak happened. How long it took from when I put the sample in the instrument until it came out the bottom. The adjusted retention time, though, is just the distance from the mobile phase time to that peak. And This is often the one that we look at, the adjusted retention time, but they both exist and they're both things that we need to know. Okay, so you can see that each of these compounds would have a different retention time. We just, the image just shows it for the unknown compound, but we can see it for the others as well. Okay, so getting us back to where we were. We were here. So we have these peaks. Now these peaks are shaped like Gaussian curves. Oh man, that was all the way back to like statistics in chapter 3 or 4. So we see that there's a highest point and then they're typically symmetrical on each side. And so these, again, they look like Gaussian curves. The broader, the wider the curves are, that's not great. We would like them to be very narrow, so like very pointy. So their width is something that we can measure. Their width is, how wide is it? That was a good line right there. We also look at their height. How tall is it? So, the width halfway up is something that is measured. So W1/2 just means how wide is it, halfway from the bottom to the top of its height. Like how wide is it halfway up? And then measurements can be made. So we see this right here, we're looking at like the sigmas, that's like the standard deviation kind of situation. So ideally, and we're going to get to this later, the more narrow of a peak, that's good. The wider a peak, that's sad. Because the narrower it is, because what happens if we think about this, the x-axis is time. So the retention time, we're going to go with like the top part of the peak. So let's say that was like 13 seconds. Well, maybe this was, 9 seconds and this was 17 seconds. So that's not a good result if there was this 6-second range where the sample was coming out. We don't know, was there a second chemical that came out at the same time? So like what we want is really narrow, and we're going to come back to that. But we'll be seeing the symbols W1/2 later. So that's just where that comes from. It's the width of the peak halfway from the bottom to the top. Okay, so the theory behind this kind of stuff with chromatography is kind of interesting. Because when chromatography has been a thing that's been around for a long time, you can do it with a piece of paper. You can put a permanent marker on a piece of paper and run water up it, and you'll see the colors change. Like, have you ever seen markers get wet? Or just like with permanent marker on your glassware when you use acetone, sometimes you see, like if it's black marker, you see other colors coming out of it because it's a mixture, and so it can be separated. So when they started this, again, the approach was interesting. So they said, between the stationary phase and the mobile phase, there's this theoretical number of plates, which are the theoretical number of equilibrium reactions that would happen between a solute, the stationary phase, and the mobile phase. So if from top to bottom, the stationary phase interacts with the mobile phase, if the sample interacts with the stationary phase and the mobile phase 1,000,000 times, then that means that would have 1,000,000 plates. The column is the thing that we're talking about. The column is that's called where the stationary phase is. So these really are theoretical. There's not a specific number. We can't count the number of equilibrium things, but they defined columns based on the number of plates. So the number of plates is how many different interactions a molecule has from top to bottom of the column of the stationary phase between the stationary phase and the mobile phase. Okay, so moving on. So if we have this pretend number of plates, well, we can figure out the plate height. I can measure the length of the column. So again, think of it like a burette. We could take a ruler and measure how long the burette was. So we could calculate the plate height by taking the length of the column divided by the number of theoretical plates. If it's 12 inches long and there are 8,000 plates, well, 12 inches divided by 8,000 tells me how many inches per plate. Okay, so that's what that second equation is. The first equation is looking at the variance of the chromatographic band. That's the standard deviation. Like if we took, like if we look back, there was a little sigma symbol on the peak that had the W's. And then X is the distance it travels through the column. So we could calculate one of two ways. What I would, although the first one is more useful in real life, what I want you to know is like the height is the length of the column divided by the number of plates. Okay. So then honestly, the number of plates is the thing that we're typically needing to calculate because again, it's a made up thing. So this is the relationship like that was on the last slide that I kind of circled. I want you to know the relationship between the number of plates, the length of the column, and the height of each plate. I want you to know that relationship because the more plates you have, the shorter the height, I guess is the relationship. But in real life, you can't know the height of a plate because, again, these plates are made up. You can know the length. So what happened from here to here and here to here and here to here is some background stuff um, that got us from here to here, which is the actual equation using values that we can get from a chromatogram to calculate the number of plates. The equation in the box, the big black box, and the equation in red are two equations to know. I will give you the equation in the black box. You will need to know the equation that I outlined in red. Okay, so looking at this, N is the number of plates for the entire column. L is the length of the column. W is the width of the peak at its base, so W 1/2 is the width at halfway up. TR is the retention time. 5.55 is there, and you're not going to worry about it where it came from. It came from things. Okay, it came from substitution. Okay, so if I was to give you a chromatogram that had a list of the retention times and the W 1/2s, I could ask you to calculate for the number of plates in that column that was used to get that chromatogram. And just so you know, the number of plates is unique to each compound because if you think about it, the retention time and the width of the peak, that's only looking at one peak. So if I have 3 components in my unknown, each component is going to have a different number of plates looking at the same column. So we're going to recognize that and then kind of just go with, we're going to focus on the one chemical that we're looking at. So here's another chromatogram. We're focusing on the nonane peak here. And so the W 1/2, which is always 2.35 times sigma. So we can, if we know what sigma is, like if we're given the standard deviation, the sigma, we can calculate that. The retention time would have to be given. And then based on this information, we could solve for the number of plates in a column. And the reason why that's an important thing, well, I take that back. Let's go forward a little bit more, and then we'll talk about why the number of plates matters, why anyone cares. Okay, so first, relationship. The smaller the plate height, so in other words, we have a smaller plate height when we have more plates. So more plates means smaller plate height, means narrower peaks. That is good because then we're able to distinguish between the different components in the mixture. So an efficient column, a good column, has lots of plates. An inefficient column has not very many plates. So we keep track of the number of plates to tell if our column is going bad. Do we need to throw away our column and buy another one? Or does this column not work for this compound? So it's kind of a maintenance sort of situation. Okay, so different solutes in the same column have different plate heights because they have different relationships, relationships between the mobile phase and the stationary phase. So to know, smaller plate height, which means more plates, equals narrower peaks, which is good. So a good column has more plates. Okay, that's a good thing. So resolution, so we're talking about these, we're going back to talking about these peaks. Resolution is looking at the difference between the peaks. If we have 3 components, we want to see in our mixture, we want to see 3 clearly defined peaks. 1, 2, 3. I don't care how far apart away they are, as long as the end of one peak goes down to down to 0 before it goes back up. What we don't want to see is that. Because sure, it's like, okay, well, there's 3 bumps, but which peak is which, and they overlap, and so how much, like it just, that's not good. So we want strong resolution, which means separation between peaks. This is bad. This is good. By the end of this, we're going to be calculating the area. We won't be calculating, but with chromatography, calculating the area under the curve is really important. And so if you don't have distinct peaks, calculating the area under the curve is not helpful. So this is just how you can calculate resolution. Using symbols we've already seen. This last one is the most useful one. TR is the retention time. Delta is so it's the change, the difference in retention times between peaks. And this is the average W1/2 between, like the W1/2 of one peak, so like peak 1 and peak 2. We measure W1/2, add them together, divide by 2. That's where that number would go. And then the delta TR would be, what's this retention time? What's this retention time? Subtract them. That's delta TR. So we want higher resolution. Okay. What we want is big differences between their retention times. And we want the peaks to be very narrow, so that way their W1/2 is very small. Okay. So again, and just an idea, the resolution, we can calculate it using that, but a number that's at least 2 is good resolution. So here's a resolution of 0.5. Now, what we would see on the chromatogram would be the blue, and that looks like one peak, but that's where not having good resolution is bad, because that is actually 2 different peaks on top of each other, and so we would never know that. The second graph looks better. It has a resolution of 1, but notice that it still doesn't get all the way back down to 0 before it goes back up. So we have some overlap down there, which is going to be hard to calculate the area under the curve as needed. So we want true separation. Resolution is separation. So good resolution means we have good separation between the peaks. So if I were to give you some different pictures of chromatograms and ask you to rank them about which one has a good resolution, the best resolution, I would expect that you could look at the picture and tell me that something that has, like this is good resolution, and something like this one is not great. Something like this one is super bad. So know that term and know how to identify it when looking at a picture.